All right, welcome back, everyone. So it's my pleasure to introduce Misha Belkin, who's no stranger here at the Simons Institute. He's done a lot of influential work, originally on learning on manifolds, and more recently on overfitting, overparametrization, generalization. I was looking at his CV trying to think of interesting things to say, and I found it interesting that his list of awards begins with second place at the Moscow Mathematical Olympiad, and most recently on his list is an ACM fellow. But I also wanted to say that, from personal experience, Misha is someone who's really nice to have around. He's very collaborative, very supportive, and very engaged. So go ahead, Misha. I'm looking forward to your talk.
Thank you very much for your kind introduction, Pauline. I'm pretty sure whatever the ChatGPT, whatever the newest LLM is far better at math problems than I am. Either. Definitely not now, and also true in high school. So I kind of tried to, my plan is sort of try to summarize some thought about this as a bootcamp on generalization, more generally the program on generalization. So I tried to summarize some thoughts on generalization and sort of maybe like to say like how we thought about generalization and what's new and why it's become such a difficult and hot topic right now. And I guess maybe to take like a very large step back, well, I was thinking what is generalization, and I think the origin of generalization is just basically it's we want to be somehow adaptive to the future. And by we, I mean like any biological organisms. And maybe the kind of very basic generalization is that basically non-generalizable properties don't survive. Now, to sort of go back to machine learning, so what do we have in machine learning as generalization? This is, of course, a standard setup. And, Nati talked about this, and other people also talked about this. So let's just think about, well, suppose I just have a classification task, right? I have some data points, and for simplicity, just assume that points in a Euclidean space, and I have labels, cat and dog or whatever. And now I would like to take this data, and I would like to make a predictor which will predict how well I do on future data which have not been seen. So you can kind of think, well, the goal of generalization is to construct a predictor which is almost as good as some sort of perfect predictor on unseen data. And the loss here, for example, could be classification accuracy, could be something different. Now, this is actually a very general setup because I didn't say anything about IID, I didn't say anything about specifics, right? So this is almost anything falls under this. So, oops, that's the wrong button. So in some sense, this is a very general and flexible, but probably too general because in this generality, like nothing can be said at all. Or very little can be said in any case. So what the kind of next point is that if you like what do we actually do in practice? And in practice, the most typical thing that we do, and well, pretty much all neural networks and many other algorithms, we do the following. We have some sort of proxy, some other loss function, which is not really what we're looking for typically. So for example, we may be trying to minimize classification accuracy in the future, but what we cannot train on classification, well, cannot or do not, I don't know. But we don't train on classification accuracy directly, we train on something else. And for whatever reason, we think that, that thing that we train on, like cross entropy, will give us good results on that task that we actually want to. And typically we have some sort of class of functions and we use some algorithm, for example, SGD, to try to find a minimum over that class of function. So that's pretty much the sort of large majority of modern methods use something like this. Now, so the key question is, well, we have this sort of abstract notion of some sort of best predictor, and we have something that we get from one of these algorithmic methods. And the question is, well, when and why the loss of our predictor is not too much worse than the loss of the best possible predictor. And I think specifically, what would we like to know specifically? Well, specifically, we want to say, well, how do you select model architectures or parameters and things like that? And actually, more recently, another key question is, well, how do you measure progress in iterative training, right? So in practice, they take some huge neural network, they train it for a very long time, and at some point they decide that, whatever, OpenAI or, your favorite company, they decide that it's time to stop. Well, how do they know this is a time to stop, right? So you want to have a proxy, not just for how well this model will do on the test data, on the sort of wild data, but also like what would happen if you train a little bit more the same model or a lot more. Is it time to stop? So this may be kind of two ways of thinking about generalization. Oops. And what is our sort of typical setting? Well, in machine learning, we like IID. Well, as Nati said in particular, like IID is kind of a very limited setting. But so in a sense, it's a great simplification of the actual problem. Well, first, we're assuming that training and test data are from the same distribution. And second, we assume, so there are really two assumptions when we say IID. I think typically we have two assumptions. One assumption is that this is the same distribution for train and test. And the other assumption is that each sample is sampled uniformly. Both, of course, are completely unrealistic in any practical situation, almost any practical situation. So you can say, well, why do we even care about something like that? And the answer is like, well, when I actually say elusive, I didn't mean that the generalization in the title of the talk. I said elusive generalization. I actually didn't say that. I didn't say that because, well, out of domain, because, all this weird phenomena that we observe. Actually, even in this setting, I think the answer to what generalization is and how to think about it is quite elusive. So I would argue sort of in defense of IID that if we cannot understand this, well, it's very hard to see how can we understand anything more complicated. And surprisingly, this is difficult to understand. Actually, it gives us more and more surprises, this setting. Okay, so now what is the talk? So first I will sort of very briefly discuss classical analysis. I'm not going to spend a lot of time, at least I'm not planning to spend a lot of time on those. Then I'll discuss a little bit also about interpolation. And then I'll talk about this kind of Grokking emergence thing, which was something I've become very obsessed recently. And you can maybe kind of think about this in classical analysis. And I say most because it's not always true, but it's sort of close to being always true. We think that training loss is predictive of the test loss. So we want to make sure about generalization by saying, okay, if I know that the test loss and train loss are close, and I can say something about the train loss, okay, then I know how we will generalize. And that turns out to be problematic for many settings, as Fanny, for example, discussed in her talk just before. In sort of this next step, interpolation double descent setting, you can say, well, training loss is not predictive because we see interpolating classifier, which actually generalize very well. But maybe validation loss is predictive. So you have some sort of validation set, or even there's a full test set, and you look at that loss and you say, well, okay, I can give the advice that, like what people do in practice. In any case, they have some sort of validation loss. And when validation loss, you train your system until validation loss kind of plateaus. And if it plateaus for a while, then you stop your training. And in this sort of third one, which is kind of recent, this emergent phenomenon, like last few years, really, what you see is that validation loss is not predictive either. Is that you basically have this plateaus of, for a long time, nothing happens, and then suddenly something happens. And it's a little bit hard to understand. I'll discuss one case of this in detail. So that's where this is the challenge and I think the key to understanding some of this phenomena that we observe. Yeah. Every sort of obvious measure plateaus. I'll show specific example. There is like all the standard things plateau. So any sort of early stopping criteria will say, okay, now it's time to stop. But then you train your, like ChatGPT for 1 more week, it becomes super intelligent, and we all die. Yeah.
I guess you don't mean like the value of the validation loss, you mean like plateauing, like the shape of the validation loss.
Neither the value nor the shape, nothing about it. Like the past is just not predictive of the future in training. You just have something which is apparently not changing as measured by the validation loss. Yeah.
That seems like the notion of predictive is different.
Yeah, this is slightly different because this is kind of predicting the future of training or what happens if you add more data to it. So it's not quite the same. But I would argue this is also generalization, right? Like if you train for 1 more epoch, is it going to make a difference or not, right? We want some sort of right? We want some measure of the future. But with good point, it's not quite the same measure. Okay, so now let me first say something about classical analysis. Again, don't think I'm saying anything new. Just some list of things which people have looked at in the past, and sort of 90s and 2000 we have like a lot of various bound-based analysis and things like algorithmic stability. Also things like, like you can look at kernel machines and then you regularize those splines when you regularize the things, and, non-parametric, or even parametric like linear regression. And, things like nearest neighbors on the derived Watson. So these are kind of a wide range of various classical, semi-classical things. Now, if you sort of look, I'll just specifically look at the bounds because it's the easiest sort of to look at, and Nati, of course, discussed them in quite depth. So what you see is that, actually, vast majority of those analyses have been of this kind of WYSIWYG, what you see is what you get form, in the following sense, that what you see on the test set is predictive of what you see on the train set. The sort of almost all analysis were like this. For bounds, it's particularly clear because you have empirical risk, which is what you see, right? Expected risk is what you get, and then you say that, well, for this class of function, my empirical risk is basically the same as the expected risk. So there is some sort of term which depends on some measure of complexity, VC dimension, for example, and you choose the number of data points. So this term is like relatively small. One thing I would like to say about this is that you can say, well, sort of, do we need a uniform? And there have been an understanding that, well, actually, if you kind of think of uniform, we say, well, why ask a guarantee for every function in your class when most functions don't perform well at all? And so you sort of a priori know that most of the functions are useless. So why not just look at the function which actually like do reasonably well on your training set? And that directly leads to the margin type bound that Peter in particular worked a lot on. And you get some sort of data dependent in this term, but it doesn't change the general form of the predictor. Now, with things like k-nearest neighbors and like smoothing splines and so on, the predictors actually of a different form. They're not necessarily like this, but you still get the same type of result that you usually in these parameters. The way you choose parameters is all that the trading loss and the test loss are not too far. Well, is WYSIWYG necessary? Well, you look at some sort of standard classical literature, and you know, like the estimate on the right seems to be more reasonable than the estimate on the left, which fits data exactly, right? Well, look at it, that's kind of reasonable, right? A model with zero training error is overfit to the training data and will typically generalize poorly. Again, this is something we believe. So this is a vibe. This is not really a, this is not something that we know. It's something that sort of seems reasonable, right? The word reasonable is important. And actually, well, it turns out that situation is much more complex than this. And I think the first one in this sort of modern setting was, in fact, by Benham and Nati, when they showed that, well, you take sufficiently large neural networks, they fit data perfectly well. This is accuracy, which is, we have to discuss the difference between accuracy and loss, but the same thing roughly would hold for loss. And yeah, you get zero accuracy on the test set, on the training set, and it performs just fine. The sort of recent famous example was from the Understanding Deep Learning Recursive Thinking Generalization paper, when they basically do the same thing with a bunch of different data sets. They show you can train them to 100% accuracy. The test accuracy, maybe it overfits, but the overfitting is not significant, or at least doesn't appear to be significant. So that certainly is something that, has been noticed empirically, and that's a real problem because, well, you can actually look at this much more systematically, and you will see that in a lot of practical regimes, the training loss is much smaller than the test loss. Now, well, going back to, like 20 years or so, that was actually the same phenomenon was noticed in those days for trees and for things like boosting. And in fact, that was kind of the basis for the introduction of margin bounds, exactly trying to explain this phenomenon. So again, it's kind of interesting, I think, from a historical point of view. It's very hard to see what is new, because you always go back and you see that, yes, this has been, but somehow, like things like, for example, autoregressive training for LLMs, right? People now, is such an amazingly powerful trick, but it's an old trick. So what is new there? It's not so easy to tell, but obviously it didn't work nearly as well. Like now it works so much better than ever before. Like why? Okay, so now let me give you a couple of exceptions to this. And one exception, it's not all classical methods have this WYSIWYG property. And one of them was, at least to me, was particularly insightful, was just one nearest neighbor predictor. One nearest neighbor predictor has zero empirical loss, but it has a nice bound. For test performance, it's bounded by twice the base risk. And that was actually pretty old. That's the classical analysis. Another thing which is, I think, was not well known, is still not well known. The first actually result of this form was this paper. They call it Hilbert regression estimate by Devroy, Gerfi, and Krzyzak, 98. And they showed that a weird estimate of this form, which it's a type of Nadaraya-Watson with a singular kernel, but I'm not going to specifically say it. It's actually consistent. And interestingly enough, the Hilbert scheme was also known before because this is the same as Shepard's interpolation. But of course, Shepard never analyzed consistency or anything like that. So that, as far as I know, kind of the only, like all the results about fitting noisy data and getting some sort of perfect statistical predictor. So I think I will skip it. So I probably don't have time to discuss. There is a kind of version of it which we analyze. There was Daniel and Partamitra, a simplicial interpolation, which I think has some nice properties. I am partial to that particular algorithm, but maybe I'll skip it because it's not very crucial. But sort of maybe the kind of upshot was, in a sense, so it was actually kind of nice because what became clear in that there were these two regimes. There was some sort of regime of this classical U-shaped curve when the complexity was relatively low and the training risk was kind of the same order at the very least as the test risk. And then once you sort of increase complexity, you go through the interpolation threshold. So your training risk, at least for ARM, becomes 0. So you fit your data exactly. You interpolate the data. And what we observe empirically, this is sort of was meant as a summary of a bunch of empirical observation, is that generally larger models perform better. It is sort of, I think we see very, very consistently in practice. And again, I have to put a lot of qualifiers here if I want the statement to be absolutely precise. But I think generally large model perform better, and generally fitting the data close to interpolation performs very well. I think this have been kind of two very generic properties of models. So in some sense, this was a pretty satisfactory picture because, well, it sort of clearly delineated the sort of traditional regime and sort of explain why we see different phenomenon between the traditional regime and this modern regime. And it gave some clues as to how this could be analyzed. Now, of course, then the question was the same, right? Well, how do you know that you will generalize well? And in this regime, it's tricky, but you can still say, look at the validation loss. In fact, that's what I said like many times. It's like, okay, well, what do people do in practice? I look at the validation loss. Let's just look at the validation loss. If your validation loss sort of stops improving, you're probably done. Okay, any questions about this? Questions or comments? Yeah. Sorry.
Stopping curve you showed earlier, was that on the validation loss or on the test?
It's much earlier, you don't have to go back.
Oh. Which one is topic?
I think it was the one you just showed. If you go back a bit.
This was a width. That was the number of parameters.
The red line there is the red line.
Oh, the red one is early stop. Yeah, I think it was probably just optimal, right, Nancy? Just best early stopping.
Like minimizing which is you're going to be the same software.
Yeah.
Early stopping based on validation, but it's not based on plateauing the validation. Like you run.
Yeah, you just run it all the way and then choose the best. Yeah, exactly. But of course, this is not a practically possible thing in general, right? Because you have to stop.
It is based on.
It is based on validation.
It is, I think. So it's based on validation, but it's the difference here is that you don't. So there's two options. What Misha wants to do is to keep track of validation, and then in a kind of an online way to decide, okay, now the validation is good enough, I'm going to stop. And what we did here is we ran until a very long time, and then we looked back and said, where should we have stopped based on the validation? Is that right? Is that
Yeah. No, exactly. And what I'm saying is that Nati could do this because, that was a relatively small setup. In a practical setup, okay, you cannot really run it. You cannot realistically run it like for infinitely many epochs. You can probably run it for like 2 epochs or something, 1 epoch, I don't know. Yeah. Okay. Go.
How do you continue to train after the training error reaches 0? Or is it just small or using momentum or something?
This is not, sorry, I didn't explain what this was. You can think of the x-axis as being the number of parameters. It's not the number of epochs. Yeah, so the larger model you can always train, and you just train until you get 0. And of course, in practice, you don't quite get 0, but you can make it very small.
Misha?
Yeah.
And also a question of how your gradient is 1, 0 when loss 1, 0. I think the answer is simply that there's a plot between 0, 1 loss, whereas the logistic loss is also not 0, right? That's
But this one, yeah, right. So if you live with something like logistic loss, you'll never completely be 0. But you can, yeah, even with a square loss, you can, yeah, it's, yeah, good point. Yeah. Anyone? Okay, so I'm not going to talk more about it because Fanny talked about this setting in her talk, and maybe I'll just sort of highlight these 2 recent reviews paper, one by Peter Andre and Sasha Rachlin, and the other is by me, sort of describing this. And so at that point, things looked pretty good. I was actually quite, well, at least like personally, I was happy. It looked like we kind of understood what was going on. And then turned out things are kind of strange. And let me just start with this. I'll get back to this. I'm not going to explain right now the exact setting. Let me just kind of give you the general overview of what this is. So on the x-axis, you just have optimization. It's just epochs or whatever steps of the iterations. On the y-axis here, you have accuracy. And this is the paper on Grokking, just 2 years ago, actually, it came out. So what they showed is the following. If you look at the training accuracy is 100% after some relatively small number of epochs, like less than 1,000. If you look at validation, the validation, actually, the accuracy is terrible. This is there are many, many tasks here. This is modular arithmetic. Again, I'll give much more detail later on. So the accuracy is basically at a random level for close to 10 to the 5, right? For 100,000 iterations. And then suddenly it just jumps. So now this is a big problem because, well, if you want to do some sort of early stopping, whether you should early stop like here, nothing is happening, right? If you early stop here, you already have perfect training accuracy. Nothing seems to be happening, so you should stop. Of course, if you stop, you don't learn. And if you run it longer, then magically you do. Yeah, Nati is skeptical. Okay, we will discuss it more. Hold sort of to your skepticism, because I'll have something much more specific about this, okay?
You said before that you have to be careful with what's like new or not new. And I mean, many of these things are...
This I have not seen before. Maybe you can point out some. I wouldn't be surprised if something like that was observed, but I haven't seen it.
That happens.
I would like if you can point me to something earlier. But for me, like actually, this was the first time, at least personally, I've seen this. Second, like the first time I've seen actually this particular graph, I kind of thought, okay, what's the big deal? We don't know the loss. This is accuracy, not the loss. Like wasn't because you see, if you look at double descent, it does say, well, okay, big system. it performs better. So it sort of stands to reason that if you train it long enough, so if you kind of think of this as a number of iteration, which is not quite right, you cannot really think about this way. But yeah, a big system will do very well, like which you train for a long time. The loss is kind of, training loss is 0 for a long time, but the test loss is still decreasing. So why is it not like that? Why is it different? So the first thing to me was like, okay, so this is just like double descent. It's something very similar to it. It sort of later became convinced that it's different. Okay, but let's hold on to this because I want to discuss feature learning, and then I'll come back and like how this fits into feature learning. Let me do a different experiment. And the experiment here is the following. So let's just take X sampled from 100-dimensional Gaussian, just a standard 100-dimensional Gaussian, and Y is the sum of the first 5 coordinates times the sum of the second 5 coordinates, right? It's a quadratic function. And actually, it's an index 2 model because it's a product of 2 linear functions. So if you're not familiar with index 2 right now, it's not super important, but it just depends effectively on 2 coordinates. But not the coordinates themselves, but 2 linear directions, right? The sum of the first 5 and the sum of the second 5. Okay? So now if I do this, and I train, say, Laplace kernel on this, I get R squared 0.25, which is not very good. If I now do the same thing with a neural network, I get 0.98, which is very, very good, right? It's pretty much perfect. So neural network learned this. Kernel didn't learn this, okay? It's R squared. So 1 is, it's like normalized. 1 is good, okay. 1 is good, 0 is bad. This is much better than that. So that's all we did. It's essentially square loss, but it kind of differently scaled. So what's going on? Why is neural network doing so much better than kernel? And what does it have to do with this Grokking business? We'll see. First, it's kind of a surprising thing because, you know, like, as far as I can tell, okay, here is another one of this. I don't know who did, like, it looks like actually there is a paper by Jason and co-authors which seem to have done the first experiment, and that was only 6 years ago, which is kind of surprising to show something very similar to this. I think it's a very recent finding, even though it seems like a very basic kind of observation. Certainly, there is nothing here which couldn't have been done 20 years ago. You don't need fast computers. You don't need anything. GPUs, nothing. Recently, there have been actually a lot of work on trying to understand why this is happening and to understand, in particular, generalization for multi-index models. Now, again, maybe I'll skip this. I'm happy to go back. Sort of, a lot of this came from understanding that in some regimes, neural networks are equivalent to kernels, but these regimes actually are hiding something quite important, and, which we call feature learning. And this regime sort of misses this key point that neural networks do something extra. But what is this extra thing that they do? And maybe one way to think about it is the following intuition. Well, if you have a neural net, so for that experiment, it's just a 2-layer neural net, okay, one hidden layer. So you multiply by your input by some matrix W1, which is 100 by D. Then you take some nonlinearity, and then you take some linear function of that. So if you think about what this does, well, W1 is some sort of filter, and it does some filtering of the input. And so one reasonable thing may be to look at the singular vectors of the W1, right? And the way to think about it, well, singular vectors are kind of hard to think about, so maybe take W1 transpose W1 and look at eigenvectors of this, and they're somehow the same as singular vectors of W1, and square root is some sort of normalization for that. Now, So maybe you can think of an MLP as, that's a kind of claim, as a low-rank filter given by this matrix, followed by some sort of nonlinearity. And I'm sort of going to ignore the details of nonlinearity for the moment. Okay, any questions about this? Yeah.
When you say filter, you mean that we're going to ignore some of the inputs? Is that what you mean by filter?
Yeah, so if this is low rank, right, so suppose this is rank 1, then I'm just going to ignore all directions which are in the orthogonal complement to that one direction. So that's basically, to me, that's a filter. You can sort of think, okay, like what does a filter do? It filters out some of the component, like Fourier components, for example. Okay, now, so that's, now I have to introduce this object, which has been actually quite, I think it's a kind of key thing. And the object is the following, it's called AGOP, for average gradient outer product. And the idea is the following. You take your predictor. Now, I'm not assuming anything about the parametric form of the predictor. So you just forget about parameters. I'm not using parameters anyway in this form. And you take gradient of that predictor at every data point. So it's gradient with respect to the input. And I'm taking outer products of gradient. So at every data point, I have a matrix of rank 1, assuming it's a single output. And I'm summing these matrices. So I'm summing as many matrices as there are data points. Now, if you think about it, this is kind of measures which directions affect, on average, the response to this predictor. And actually, it's easy to see that if you have a multi-index model, so what's a multi-index model? Multi-index model is simply y equals f of mx when m has a low rank. So if it's rank 1, this would be like a single index model. So, and then of course, well, if you have this function, you notice that if m takes that direction to 0, right, if something is in the kernel of m, it doesn't affect the output. So in principle, I should try to ignore that as much as possible. So if I somehow can identify the kernel of this matrix, the zeros of the zero set of this matrix, I can project onto the orthogonal complement to that, and this will be the only relevant direction. And presumably, well, hopefully the number of these relevant directions will be small compared to the total number of directions. So why is this interesting? Because, well, for a model like this, top eigenvectors of this AGOP matrix actually span the same set as the range of M. This is not a new idea. It's been, around for quite some time, actually. Now, you can kind of think of this AGOP locally as just like at every single point, it's just a local projection onto the gradient of f. And now what I'm saying is that like I'm going to average all of these projections, and hopefully when you average this projection, they share something in common. That may be another way to think about it. But let's take one step forward and let's look at that experiment from this point of view. And if you look at, so you train this neural network, we train this neural network, and we look at the AGOP of this neural network, and we compare this to this W1 transpose matrix, and you see, of course, that both this very nice low-rank structures appear. And what would you expect if you have a perfect model, right? You actually only have two non-trivial directions. You can think, well, there are these two blocks, but these blocks actually hide the fact that the blocks are constant blocks in the perfect model. So in fact, this is a matrix of rank 2. But it's a 100 by 100 matrix, but the rank is 2. It's a little hard to see this. What you see is that there are two blocks 5 by 5 in the corner. But you sort of visually, if you just look at these two things, you see these are very similar matrices. So again, I'm kind of, and now here is a kind of impressive thing about this type of matrix. If I just use now, imagine I take my data and I forget about the model itself. I just store these two matrices. So I train this neural network and I completely forget about it except for these two matrices which I extracted from it, okay? Now I'm going to filter my data using either this matrix or that matrix, either AGOP or this neural feature matrix. And now I'm claiming that after filtering my data, actually all the methods are about the same. So for example, a kernel machine, so remember, initially when I trained neural network was way better than the kernel machine, but actually after I filter with this, the kernel machine and neural network are actually about the same. Actually, kernel machine is even slightly better. It was very similar. And another thing to notice is that as expected, they look similar and they actually act similarly, that both AGOP and NFM give you roughly the same performance. On the other hand, if you use no filtering at all, then kernel machine completely fails. And neural network nearly fails. Now you say, well, didn't we just train it using a neural network and it was okay? Oh, that's because this is far fewer samples here. That was 4,000 samples, this is 500. If it's 500 samples, neural network doesn't do well. So the upshot of this is that extracting this AGOP matrix is basically like all the work of training the neural network is effectively extracting this matrix. Once you extract this matrix, you can pretty much use any nonlinear method and you will do quite well with far fewer data points, only 1/10, 1/8. Okay. So now I'm not going to go deeply in this, but we sort of argue this is our recent paper with Aditya Krishnan, Daniel Beagle-Hall, and Party Pandit. And we actually argue that effectively what is happening in training neural networks is that it's learning this type of matrix. So this is the feature matrix of this neural feature matrix, and this is AGOP, and basically it's the same thing. Now, when I say the same, it's not mathematically the same, it's empirically the same. This is observational for different types of neural network. Now, what's the upshot? Now, I would like to sort of give you some sort of alternative to neural network, and you will see in a moment why I think this gives us a very nice setting to study emergence. So if you think about from this point of view, you can say, well, okay, maybe neural networks are kernel machine plus some sort of relevant feature learning. And this relevant feature learning is, at the very least, for the basic architectures, it's implemented simply by multiplying by a matrix and maybe low-rank matrix. So you would like maybe something like this. Some low-rank matrix, you filter your data, and then you apply a kernel machine on top, and you want to learn both the filter and the predictor. And interestingly enough, neural network does it by gradient descent, but we don't have to do it by gradient descent. We can actually do something slightly different. And what we can do is the thing we call recursive feature machines. You build a kernel predictor. You compute this filter from the predictor, you filter the data, and then you recompute the kernel on the filter data, and you repeat this a number of times. Okay, is this clear as a process? So fit your data using a kernel machine, compute the AGOP matrix from this, and this is probably not a very good AGOP because your initial estimate is not very accurate. But after you refilter the data, you kind of hope to bootstrap that you learn some structure in the data. Questions? Yeah. So I would like to do something like what neural networks do, but I don't want to use gradient descent. I want to use basically a different method which allows me. The gradient descent has a number of issues. Which makes it tricky to think about. So I'm kind of thinking, okay, my neural network learns two things, right? It learns some sort of filter and a predictor. So how would I try to learn this? Well, you can, instead of gradient descent, you can try something which kind of looks like EM type of algorithm. I build a kind of candidate predictor. Then I build a filter from this predictor, I refilter the data, and I build the next predictor which based on refiltered data, which is presumably better. And then I repeat this. So I'm kind of iteratively refining the data. So I'm kind of ignoring all of the predictors except for the last one, but my filters keep improving.
Like some important direction of the data.
Yeah, so if it's a low rank, if my data is actually low index model, then this thing should be low rank, and I would expect that the rank of the thing will drop. So if it's like a single index model, eventually I hope to get something which has rank 1. We will see. It's more complicated than that. Unfortunately, that's not quite the story, but that was the hope. Yeah.
Can we think about learning in metrics as some sort of particular case of learning the correlation structure between the input dimensions given like the
Given the output, yeah, it's some sort of non-linear. Yeah, it's exactly non-linear version of supervised PCA. Yeah, it's exactly that. Yeah.
The alpha i's, how do you select those weights? Using like
So when you train a kernel machine, you just solve a linear equation. So that's what makes it very nice. It's just so in practice, this is a linear solver, and then this is just some formula for this. So linear solver, then formula, then linear. So it's an iteration of linear solvers. So it's completely clean, right? There are not many moving parts here. And I didn't discuss this alpha. Let's just ignore alpha. Notice that the rank of this matrix doesn't depend on alpha.
Yeah,
Oh, I'm sorry. Yeah. This alpha is completely different from that alpha. Those two alphas have nothing in common. Yeah.
When you apply this procedure, do you see some sort of convergence in like the filter or the features, or how do you determine what?
I'll discuss this in a second. In fact, you will see. Yeah. So this actually works quite well, and you can see that it works on practical examples. I'm not going to show those examples, but what I want to show you is something which is like a little bit Grokking-like. Yeah. Remember?
the kernels make a difference, or like whether like is it okay whether I use Laplace or RDF or like
a few months ago I would say no. Now I say yes. We actually, for practical data, we most often use Laplace, but it turns out that for Grokking modular arithmetic, for whatever reason, Laplace doesn't work at all. So, yeah, I don't know why. So clearly it makes a difference. Okay, so let me give you this example, and then you're like, okay, like, well, what's so special about this? And then I'll show you the actual Grokking modular arithmetic, which is mind-blowing, I think. Which actually has many aspects of this, but it's so much more extreme. So this example is very simple. This is just two classes from CFAR10. And we modify that by putting like a little star here, and the color of the star encodes the class. So it's a really easy problem if you know to look at. At first, it's a low index model, right? Because if you just look at one pixel within the star, that's a perfect predictor for the class. Second, it's a really easy problem if you know what to look at, right? But if you don't know to look at it, it's not so obvious what should be done, right? Because how do you know that the star encodes the class? So your neural network doesn't know this. Okay, you run a neural network and you see something quite interesting. You see that after about 90 epochs, the training accuracy is already close to 100%. But the test accuracy is actually pretty bad. It's only like, whatever, 80 something percent. And as you continue training the thing, the test accuracy, of course, cannot go any higher than 100%. It's perfect. But the training accuracy just keeps improving. I'm sorry, I said it exactly the wrong way. So switch everything that I say. It's all modular So the test accuracy keeps improving, and you get very good test accuracy after like 150 epochs. Now you can ask why, and actually if you look at these matrices, you can just visualize them, and you see that yes, it identifies a star in the AGOP matrix, but it's not very clear. But after like another 100 epochs or so, it actually becomes much cleaner. Okay, yeah.
You said the same thing. Secondly, if you measure the margin expand.
So let me postpone the margin discussion. The loss in this case, you can say, oh, maybe it's something about the loss. I'll get to actual grokking when you will see that loss tells us nothing. But let me give you slightly different even for this. Like we can do the same thing with RFM, right? Exactly the same setup. With RFM, actually, interestingly enough, it just takes 3 iterations. So the first iteration, after I just fit the kernel, the result is terrible. It's under 60%, right? Like just a little better than chance. But you already see that the star is very clear. After the second iteration, it's 95%, and third iteration is like more or less perfect. So you can see that these things have been trained to have 0 loss. So they actually have 0 square loss, the exact interpolants. So training loss predicts absolutely nothing in this case. And you can see that, yeah, it's very similar to this, except it's kind of accelerated. Instead of like whatever, 100 epochs, you need 3 iterations. Okay, so you can say, well, this looks a lot like grokking, but it doesn't really okay, it's still like improving slowly here, and you can kind of see that it's, maybe you can explain it by some sort of loss. We will look at the grokking in a second, but let me sort of summarize this. First, clearly, feature learning in this setups is different from fitting training data because all of this model fit training data equally. They're all perfect in fitting training data, which is why I like RFM much better than neural nets, because with neural nets, if you fit data perfectly, of course, you cannot train anymore. So you always have to have some slack in training data. But with these things, you just fit exactly. And you see that it's not about fitting, right? It's all about the inductive bias. Second, loss is not a proxy for accuracy at all, because loss here seems to have nothing to do with accuracy whatsoever. Nice thing about RFM, it sort of decouples feature learning from optimization. And the kind of natural way you would say, okay, this is all very nice, but it's pretty clear what's going on, right? Because this is a low rank matrix. And if you observe what's happening to AGOP, the rank of it is dropping. I actually didn't show it here, but it's learning some low rank predictor, right? So it's a pretty good story. And it is definitely true that you're learning low rank predictor here. So low rank maybe is a pretty good proxy for generalization, right? And that's what I thought until recently. Now let me go back to grokking and show you that low rank is not actually. It's not enough. It's something, but it's not enough. Okay, any questions about this? Yeah.
I guess is the argument here that there is no connection to gradient descent here, or is there like kind of?
Well, I wouldn't say no connection. It's just a different mechanism. I mean, what we're using is not at all gradient descent. Of course, there is some connection because it shows similar property. So the argument is that like this different mechanism have the same property or similar properties to gradient descent.
Is there like a literature in like trying to like connect, like, because I imagine like your argument is like this may be what's going on under the hood, so.
I can, maybe we should take it offline, but yeah, we basically can show like there are a bunch of things that this model show which are very similar to what, like neural collapse and some other stuff. So it does look like they capture a lot of properties of neural networks. But let me get to grokking, because grokking is an example of exactly this. And it's a somehow very strange example, yeah.
This might not be a little relevant, but like I was wondering, like, in terms of robustness, like if you had a star which was like spurious, do you think like like which one would be like more robust? Like, will you pick that point also, or what's the intuition?
Yeah, actually, it's quite interesting. Maybe I should also take this offline, but we did those experiments. Like you, for example, there are like very interesting examples when the prediction for, what was it in one of this data sets, basically when you try to identify like faces, and one of them is like lipstick, right? Whether the person is wearing lipstick. And the interesting thing is that the predictor for lipstick is actually the eyes. It's not the lip area. So if you can remove the lip area completely, it almost doesn't affect the accuracy. But if you like block out the eyes, it dies. So yeah, there is some sort of pretty interesting robustness, which I think they're kind of similar between these two things. Okay, let me now go back to Grokking, okay? Go forward to Grokking. So first, what is the problem? The problem is to predict modular arithmetic, and let me sort of tell you what do I mean exactly by this setting. So I'm giving you a bunch of examples of modular addition, how I encode the first, so a plus b equals c. So for example, 1 plus 2 mod 3 is equal to 0 would be encoding as, so 1 is encoding 0, 1, 0, 2 is encoding 0, 0, 1, and 0 is encoding 1, 0, 0. So the pair would be in the input is 6-dimensional, the output is 3-dimensional. Okay, and you're giving some sort of number of these things. So in principle, there are p-squared, these pairs, and I'm going to give you your like 30% or 50% of all possible pairs and test on the remaining pairs. There is no real validation here, it's just a test set. It's a finite set, not just, there is just a finitely number of the things. Mod 3 is, of course, too small, but it's like, say, mod 101 or something like that. So you have like 10,000 pairs. Okay? So that's my training set is basically a bunch of these things, these pairs. They sample randomly. Okay, any questions? Is this clear? Now, of course, what I want to do, I want to build a predictor for these things. Is this clear? So this encodes 1, this encodes 2, and concatenate them. That's my pair. You can think of this as a sequence. In fact, the first paper, I think they used the transformer, but you don't need a transformer for this. Okay, now let's see what happens. So this is the number of iterations. This is with RFM. So notice that the square loss is identically 0. So this is a number of iteration, and this is the square loss, and this is accuracy, okay? So the square loss is identically 0 because you always just fit exactly. The accuracy, of course, is 100%. Now this is on train. On test, you can see that for the first roughly 10 iterations, nothing happens. And then very quickly in the next 5 iterations, it just goes to perfect. So 10 iterations, there is no improvement. And then within a few iterations, it learns. Now, you can say, well, okay, before I show that, well, so what is happening, right? What is the progress being done? Because this progress clearly is reflected neither in accuracy nor in the loss, which is more surprising, because you can think, okay, accuracy is discrete, but the loss is continuous. So this should work. And actually, something pretty remarkable happens if you look at these matrices, at the AGOP matrices. And you can see that what is happening is that the striped structure starts forming. And after about like 10 iterations, it's kind of pretty perfect. Basically, after like at 15 or 30, you cannot visually see much difference at all. So it looks like there is some sort of steady progress in the formation of the stripes. But this is not reflected at all in this thing. Okay? Oh, and I should say this is, we just put up this paper like a month ago. It's this, with Neil Maliner Daniel Beagle, Howley, Binju, and Adit Radhakrishnan in Party Pandit. So this is what we see. Okay. Now, is this clear? Because in some sense, this is what is happening. Yeah.
So you mentioned the RFM you can still train RFM even with the training losses.
Exactly.
Can you elaborate a little bit more? Because RFM, you need to evaluate the gradient.
No, you evaluate the gradient with respect to the input. That gradient is never zero. You don't evaluate with respect to the parameters. So it's loss zero. You compute the gradient with respect to the input, use that as a filter, then refilter the data, and refit. Hey, is this clear? So something I think this is like extraordinarily remarkable, because one thing is that like, where is this coming from? Because there is no signal coming from the loss, right? We're training using effectively the loss, like we're fitting the loss, but there is no signal coming from this. Nothing is changing here. So why is this improving? I actually don't know, but like I don't have any answer to this. But yeah, this you can use either Gaussian or quadratic kernel. They're both similar. Laplace doesn't work. In fact, we couldn't get it to work for a long time because we were using Laplace. Don't ask. Yeah.
The final solution somehow, but why does it actually get stuck over there? Like why does
So this is this was an explanation for one potential explanation for Grokking, that it somehow SGD. Notice that we don't have anything like SGD. Nothing gets stuck here. And if you look at this, it doesn't look like anything is being stuck. I'll show you actually some more direct evidence that it's not getting stuck. Our method definitely doesn't get stuck. With neural networks, it's a little less clear, but it also doesn't look like it's getting stuck. I can show you some progress measures for neural networks.
You see the squared loss is monotonic. I mean, it's very gradually decreasing.
The square loss here is constant. So you can say maybe it's stuck. Yeah, here it's clearly improving, yeah. But there it's constant. So maybe it's stuck, but it's not, because there is some other measure that you can. Okay. Now let me point out another thing which is very interesting, because this is for addition. This is modular addition task, mod 67 or something like that. And okay, you just look at this and you see stuff. Now you do the same thing for multiplication, and the results like this. These two curves are exactly the same. I'm not showing you, but they look very similar. You cannot really tell. Let me show you, however, the pattern of AGOP. This is for addition, I just showed you. What happens if you do the same thing for multiplication? This is what you see. Okay, any guesses what this is? Random, right? Random? No, it's not random. If you reorder this is what you see. It's actually the same circulant matrix. But I didn't explain what circulant was. So circulant, this you can see the diagonals are kind of constant here. So circulant is constant diagonals, but it's a little stronger. It's like a wrapped diagonal, which is constant. But if you just want to think of constant diagonals, it's close enough. But you can see this has exactly the same structure as that, right? But this looks like it has no structure. So you cannot just look at this and say this. You have to do something active, like reordering. Where does this reordering come from? Well, let me just explain the reordering. What is modular addition, right? You have z over, this is modular prime, z over pz, right? And if you take z over pz, you have a generator which is 1, and you're encoding them like this, like 1 gets encoding, sorry, this is 0, like 1, 0, 0, 0, then 2, next one gets encoding as 0, 0, 1, and so on, right? This is like 1, this is 2, and so on. Mod p, of course. Now, what about multiplication? Well, this is z over pz star, the multiplicative group of this. Now, this, of course, doesn't have 0 because 0 is not a, you cannot divide by 0, right? But does anybody know? Like, I'm sure many people do. Anybody wants to say what the structure of this group is? It's a cyclic group of order p minus 1, right? So actually, this and this look almost, they're almost exactly the same. Now, of course, the generators, like if you don't know what the generators are, you will see that this is kind of random order, right? If you don't know the multiplication of the group. But if you take a generator of this and then reorder the rows in the order of the generator, this is what you see. So now this is actually bad. I mean, this is good because, okay, this is great. Like we can reorder it and you see this beautiful structure. Why is this bad? Because if you just look at this, I have no idea about the structure of the multiplicative group of z over pz. I mean, okay, I know it because I took some group theory class a long time ago. But, you know, like how do you go from this to that? So it's very difficult, I think, from this to know that that's the right thing. I'm just saying that, yes, for this case, it's a relatively simple fact from group theory, so we can kind of figure it out. If you have something like that, but more complicated, how would we even like start thinking about it? Like, where would that knowledge come from? And somehow neural network doesn't care because it obviously just, it doesn't know and it just does whatever it is, or RFM. But there is some sort of structure which seems very difficult to interpret. Okay, in any case, be it as it may. So we have the standard progress measures. And you'll see that accuracy loss are all pretty useless. Now, you may think this is a multi-class problem. You may say, well, what about like looking at the correct predictor, right? Because they're a multi-class. When we average the prediction, so when we compute the loss, we average of all predictions over classes. So because there are like 100 of them, this will hide a lot of structure. So maybe the correct prediction is improving slowly with iterations, but because you're averaging over like 100 or some large number of classes, you cannot see it. So we looked at the test loss of the correct output class, and you see it's exactly the same with that. There is no improvement there either. So that's not an explanation. So that doesn't work. Now, there are these hidden progress measures that you can come up once you know the solution. And one, you can look at circular deviation. What is circular deviation is basically just looking how far the thing from constant on the diagonal. Just compute the variance over the diagonals and average it, normalize it. And you see that if you look at that, you see that actually that is like perfect. It's like linear. So every iteration gets you more and more circulant. So if you know that circulant is your target, then you're done. You can kind of look more general. You can just look at the alignment of the AGOP between your initial model, your model at time t and the final model, and that also grows like close to linear. So there are these hidden progress measures. They're actually quite unsatisfactory in a sense. Yeah. I'll show in a second. Well, more than a second, in a minute. So these are nice in this. They really do work. They're quite unsatisfactory because circular deviation actually like requires you to know that it's going to be a circular matrix. How do you know? Well, because you looked at it and like we figured out it was circular. What if it was multiplication to start with? For multiplication, we have no idea that it's circular, and it required this extra insight about generating group, the generators of the multiplicative group to know this. So this is kind of requires like knowing the answer already. Once you know the answer, yes, it's a good measurement. AGOP alignment is okay, but it has the same problem. You somehow have to have access to a trained model. Yeah.
Of the AGOP updates.
That's effectively this. AGOP alignment is effectively convergence of AGOP, which is fine, but you don't know that the end result is anything good, right? Maybe you didn't learn anything useful. So, I mean, this is, I think, the best we have, but it's, I would like to look at this, something like this, right? I would like to look at test loss. Yeah. No, tested validation is the same. I mean, this is better than validation. The test is already like this. This is like really looking at the at all of the examples. You cannot beat this. Right? This is actually on all of the examples. This is like true loss.
Validation accuracy can predict the test accuracy.
Yeah, validation accuracy and test accuracy would be the same, but the test accuracy itself doesn't predict itself. Right? The test accuracy doesn't predict the test accuracy. That's a problem. Like you go through iteration and it jumps. So it's not that validation doesn't predict test, it's just test is not indicative of the test. Yeah.
This is an example you mentioned. Rank doesn't help.
The what?
Rank.
Yeah, rank. So yes, the quick answer is these are all high rank. It's not low rank. I'll say I'm kind of running out of time. How much more time do I have? Okay, yeah. It's not a low rank solution. This is all high rank. Yeah.
What about just the deviation between iterates of the AGOP, like as you're measuring AGOP at time t plus 1?
We haven't actually measured that, but given that it converges, I think it will go to 0. But that is not like that would just say that we converge somewhere, right? It doesn't tell us anything about what we want to know. Maybe that's a good yeah, could be. So I think this is the best thing we probably have at this point, because this is general. It doesn't require you specifically circling, and it tells you something, but it's somehow very unsatisfactory because it learned this very specific thing. Now, is it just circulant? And the answer is yes, I'm not going to go. So you can kind of do like a random circulant map, and if you just map your data with a circulant and do a kernel on top, it works very well. So there is nothing more than a circulant there. Random circulant basically covers it. It really learned exact structure. Now, neural networks. So what we can show is that neural networks actually learn something very similar. If you look at these are the AGOP matrices of neural networks, and you can see, you have to reorder them the same way. You can see they look quite similar, a little noisier, but now if you look at the accuracy loss and loss of correct output class, the correct logit, basically the same thing as what we observed. The problem with neural network is that the training loss cannot be 0, because otherwise you wouldn't be able to train. So you never can completely disentangle the training loss from this effect. But if you look at circulant deviation, you can see it's actually first couple of epochs is stable, and then it goes down like almost linearly. So it's quite nice. And the same thing with AGOP alignment, it also goes up linearly. So it looks very, very similar. This is for addition, for multiplication and so on. It's kind of similar, not exactly the same. So neural networks arguably learn the same thing. Now, I'm not going to there is actually a very simple low rank implementation that you can think of. So it's in fact an index 4 model that will implement this thing. So my first thought, of course, was like, okay, well, we know that this neural network can learn low rank model, RFM can learn low index model. Therefore, that must be what this thing is learning. So yeah, I wrote it down. Okay, it's rank 4. So we looked for rank 4 structure. That doesn't look any like rank 4 structures. No, that's not what it's implementing. So this was a kind of, this low rank thing was misleading. Okay, maybe I'm running out of time. I kind of wrap up. So a couple of sort of overview slides. So Grokking learns circulant features, and in fact, we can show that it's learned some sort of, some version of it learns Fourier multiplication algorithm. I'm not going to explain what this is right now. But yeah, basically you do Fourier transform and you do some sort of multiplication in the Fourier domain. And so in a sense, this is kind of interesting because you do get out of domain. So this is trained on this kind of Boolean inputs, right? It's on a cube. But once you learn this algorithm, the algorithm actually works on any real numbers. You can use the same algorithm. So you get this out of domain generalization for free. Clearly not specific to neural network gradient-based method, that's obvious. Not predicted by test or training loss, so all the standard things which we like, they don't really work. I think there is strong evidence for emergence, because we don't know any a priori sort of generalization measures. When I say emergence, I should just say that to me, emergence is when you like train a neural network and something changes very rapidly. It learns from like, it goes from not learning something to learning something. There are different definitions in the literature. I'm not going to go there. Feature learning seems really mysterious because what process can learn both low rank matrices and things like circulants? Right now, they don't look of the same type. Like what is common between low index model and models given by circulant embedding? I don't know. It's maybe that's the key question. Okay, is it a mirage emergence? Well, clearly it's not a mirage because, so there was this kind of paper when they sort of argued that maybe it's a mirage because when you look at the, for example, test loss, that can be continuous, but in this case, the test loss has exactly the same properties as accuracy, so there is no tension between continuous test loss and discontinuous accuracy in this case. In fact, that was also shown for things like sparse parity and other things as well, so it's not even like similar observations in those papers. I think the difference with our setting is that our training loss is always 0. So training loss clearly cannot be a proxy to anything. Okay, and finally, concluding thought, I think there has been like a lot of recent evolution in how we think about generalization, even the ID model, right? From kind of this classical bounds, which are WYSIWYG, to, you know, things like interpolation, double descent, and now this strange Grokking phenomena. And this has been driven primarily by empirical evidence. I think people observe something and we try to explain it, and we see, we try to understand these remarkable things. Generalization theory very clearly cannot ignore feature learning. It's very clear that a lot of this phenomena are about feature learning, and low rank feature learning is not sufficient. So finally, I think there is both a challenge and an opportunity. I think the right ID generalization theory may just explain out of domain learning, right? Like how do you do something IID and then you get this Fourier multiplication algorithm, right? It just appears. Well, how? I'll stop here. Thank you. It doesn't drop at all. No, the spectrum, it's not low rank. The spectrum doesn't drop.
The spectrum can drop without it being low rank.
Oh, how fast? I don't know. It's like nothing special. It's like there are like 30 large eigenvalues or something. We looked at it. We couldn't say anything. Yeah, it drops. You're right, but it's like nothing remarkable.
I mean, just more probably just answering your question. You can see a very similar phenomenon even just in logistic regression, linear logistic regression. Because what happens is you get, and it's different, it is a gradient-based algorithm, but you get zero training error very quickly, but then you very slowly move towards the max margin solution. And when you need the max margin to generalize, which is a very typical situation, then if you look at the graphs like this, you'd exactly see the situation that the training accuracy reaches 0 instantly, pretty much, and then remains at 0, and the test error is at 50%, like null for a very large time, and then drops. So, and I think the basic mechanisms in both cases are similar. That what's happening is what you're improving is not the training error, but you're reducing model complexity in some way that. In that case, I understand exactly. In here, I don't understand exactly what is the model complexity that's being.
No, that's exactly the low rank thing, and that's what I was thinking. Okay, it's learning something low rank. So model complexity is given by low rank, but I don't know what this thing is doing. This is very strange thing.
This is another model complexity, which I don't know what it is.
And this model complexity has both low rank and this weird thing built into that. So what is it?
This idea of the Grokking itself, the fact that explaining this plot, you don't have to go beyond linear regression to logistic regression.
Just the slow. Yeah, that's a fair point. Yeah. Yeah. That's why I was like, initially I looked at this low rank thing and I think it was kind of like, yeah.
Thanks, Misha.
Thank you. Thank you for your patience.